Yeah, I do find it strange that in PChem, you know that two electrons repel each other and they'll fly apart. And I say, why? You say Coulomb's law, and I'm like, good enough. But again, where does that energy come from? And the answer is because they're exchanging photons faster than the time uncertainty principle, so you can't observe it, but that's why they repel each other. They're like being pushed apart by photons. A lot of physical chemists don't know that. And I don't know if anyone knows that because I'm not sure if that's really true. We have a model that explains everything, but you could never prove it because of the time uncertainty principle. That sounds hokey. Anyway, we also talked about fermions and bosons. Fermions are electrons. You know that those cannot be in the same state at the same time. We get around that for hydrogen with 2s electron, or helium with 2s electrons. Well, those are in the same state. No, they're not. One spin up, one spin down. That's how we get around that. Bosons can have an arbitrary number of whatever's in the same state. Those are molecules and photons. So we're going to do photons today. I did want to motivate you a little bit on what the heck this is useful for. For one, I mean, if the physicists are correct and this is how everything works, let me give you another example. So this is a inorganic lattice. I'm not just trying to represent a simplified like slice of an inorganic lattice. Certain inorganic lattices, such as some ceramics, are one thing is coordinated to 4. So some ceramics, copper-based ceramics, and guess what? If you add or subtract electrons from those copper-based ceramics, those are where you get high-temperature superconductors. By high temperature, I mean liquid nitrogen temperature, right? Okay, now here's how this works. All high-temperature superconductors are antiferromagnetically coupled, and that means that if I'm up, then someone else needs to be down. Okay, so down, down, down. Now let me point up. Let's see. Then this guy needs to be up, right? And actually, you know, I tend to forget how to represent this. It's a little bit easier if you do this on a Kagome lattice. And again, so this is a representation of a mineral that could be a high-temperature superconductor. So sorry, I forgot how you do it on a square lattice, but on a Kagome it's very easy. Okay, so spin up. Now remember, if we're antiferromagnetically coupled, the other guy is spin down. These are copper atoms, right? Copper can have extra electrons. Okay, now you see where I'm going with this? What's the third one? Is it up or down? It's down?
It can be both.
Well, no, it can't be both. It has to be one or the other. It's a fermion. If it was a boson, I guess it could be. We could just have 2 of them. It's up or down. Which is it?
Up.
Okay, if it's up, it's okay with this one, but not that one. You see? You have to be antiferromagnetic, but you got a problem. You can't satisfy both electrons. So this is called spin frustration. It sucks, basically. It can't satisfy its other partners. So which is it? Now remember I was saying that when you make high temperature superconductors, what you do is you have to, let's say you p-dope it, that would mean that you remove electrons. If you add electrons, you n-dope. If you remove electrons, you p-dope. And you can do that by using ionizing radiation or chemical reductants. And what happens is, if you want to think about electrons, as much as I don't know which way this guy is up or down, you run into another problem for conductivity, which is that if you're going to move this electron around, you have to move in pairs, right? It's kind of impossible not to, and that's because of the spin frustration problem. All right, so what ends up happening is, I'm just kind of going blah, 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 is you can do things like this. You can have a little fluctuation in the lattice such that these two guys end up coupling together, and instead of getting 2 fermions, you get a boson. So just like a proton has a fermionic nucleus and a fermionic electron, when you put the 2 together, the total spin is 0, and now you've got yourself a boson. 2 electrons can do that as well, it's just more unusual. So if I have a spin up electron and a spin down electron, and they kind of couple together and become one thing, just like a hydrogen atom is one thing composed of two, whatever, it's one thing, two electrons can couple and become one thing. If they're spin zero, they're bosons. If they're spin zero and bosons, they undergo Bose statistics instead of fermion statistics. That means that they can undergo a condensation, where all such pairs, which are called Cooper pairs, all such pairs are now in the same state, and that's called a Bose-Einstein condensate. That is where you get superconductivity. And again, it's because it's a boson. All these things are then in the same quantum state, which you could never do with fermions, but it's not a fermion. And then because of that, it's a Bose-Einstein condensate, and those move as superfluids, which is what the superconductor is. Anyway, so these are Kagame type inorganic lattices, or models for cuprate ceramics, which are what is actually commercially used. So I just it's really easy to remember how spin frustration works in a Kagame on a square lattice. I always get confused how that works. Anyway. So I just wanted to point out why you might care about these fermion and boson stuff. You do need to know that as well. See, the last thing we're also talking, so let me get on to what we're really talking about. Bosonic light, and I started out with a cavity, and we'll make it a laser cavity, because what is really important to know about light is, and remember that you have to have some multiple of a wavelength of light fit inside the cavity, not 3/4 a wavelength. You got to have this, or what is that? 3/2 a wavelength, or here we go. Or that works anyway. Those wavelengths work. Those are resonant modes of the cavity. Now, so that's one thing to remember, that optical objects have a certain number of allowed modes, and that's a very fancy way of saying only certain wavelengths of light fit inside said optical object. Now, for every mode, you have a photon. Maybe you have no photons, maybe you have one photon, and that would be it if light was a fermion. But you could have 2 photons, 3 photons, 4 photons, because light is a boson. And that affects how all optical objects work. So to describe a blackbody radiator, in other words, a flash bulb, or the sun, same thing. They work exactly the same way in terms of their light. Yeah, that's what we're going to do. So, and you can build more esoteric optical objects, such as etalons and whatnot. Okay, to do this guy, we like to use, as always, we pick a statistical ensemble that's easiest. It is easiest to work with I'm obviously working the canonical because I wrote the big letter Q, so I'm trying to solve the canonical partition function. As always, it is the sum of states, either the energy of the states, and I will now insert boson statistics. And what I have to do is I have to write technically an infinite number of sums. These are modes. And the damnedest thing is, it's an infinite number because there's a limit on the long wavelengths. You can't get a wavelength longer than the object, but you can fit arbitrarily shorter wavelengths. Notice how I started long and I drew shorter and shorter and shorter? Well, that goes on forever. Anyway, so I'm only going to write three modes because I just can't write forever. And then I've got either my beta energy of those modes, and the energy, of course, depends on the number of photons and the energy of said photon. Of course, that's Planck's constant times the frequency. And I'm just going to call that a little e because, again, I just don't want to write h. Little Planck constant nu for frequency over and over and over again because it just drives me nuts. And again, remember, this goes on forever. Okay. Now, it turns out that barring the fact that there's an infinite number of sums, and remember that, what you've got, e to the 0 plus e to the 1, e to the 2 times e to the 0, e to the 1, e to the 2 to infinity times e to the, right? So you actually have kind of a horrible mess in here. Technically, it's infinitely big. However, one reason that the canonical is is great most of the time, that's why it's usually our friend, is that exponential things have, there's so many math when it comes to e to the blah. Yeah, between natural logs and just so many math that these actually end up usually being much easier. So as much as this is a crazy sum, it ends up being a multiple of modes, of all the J modes, where we're summing the bosonic occupancy. Okay, and again, J refers to the mode, and I'll use like 600 nanometer mode. I like red lasers. I got my PhD with a red laser. So these are the same thing due to math of E. And we'll do some tricks with natural logs as well. That's coming up. Okay, and remember I'm actually reviewing last time, because the occupancy can be 0, this ends up being e to the 0, the first term of the sum of e to the 0. Then I'd have e to the minus beta of whatever jth mode this is, and then I would have e to the minus 2 beta, energy of the jth mode of the 600 nanometer. I'm just going to use 600 nanometer. I'm going to say that there's a 600 nanometer mode. Okay. And then we recall some of our high school Taylor series, and this ends up being 1 over 1 minus e to the minus beta. Okay. So it's a Taylor series, and it turns into this. Okay, so what? That means that the partition, the canonical partition function, is the multiple of something. So at this point, it's really not bad at all. There we go. And again, remember the energy is actually h frequency. That's light for you. H, speed of light over the wavelength, right? Yeah, that's frequency. Okay. Okay, so what? So again, we're going to do Blackbody Radiator. If it bothers me, it's not perfect. Anyway, I wanted to do Blackbody Radiators because back in the day, when they were figuring out basic thermodynamics and they started figuring out about light as well, they tried to apply their rudimentary understanding of thermodynamics to light, and they got a spectacular failure. What happened was, here I'm going to do wavelength, which is c over the frequency, right? And of course, remember energy. So remember, wavelength is 1 over energy. It's one of the biggest things people, if you were at your prelim and you forgot that, when we do absorption spectroscopy in the visible, and we tend to do this in nanometers, this is high energy even though it's to the left, and to the right is low energy even though it's to the right. That I see people that screw that up, and that's bad. Anyway, okay, so what they thought back in the day, this is around 1900, was that they actually tried to apply the equipartition theorem to light in a box. And that meant that you have basically 1/2 kT of degrees of freedom for every photon. Where they really blew it was that they assumed that every photon that can exist in a box does exist. The problem is that, again, that's an infinite number of photons. And we count to infinity using shorter wavelengths, which have higher energy. So what they determined was, now again, there's actually a small intensity at low energies because you can't fit as many long wavelengths in a box as you can short wavelengths. So there's a rise due to the number of waves that fit in the box. But the thing is, it kept on going. And if the output is the integral, is related to the area under the curve, which would be the number of photons, they calculated that there's an infinite amount of, as soon as you built a black box and it was something other than 0 degrees K and you drilled a hole in it, infinite amount of energy would shoot out and destroy the whole universe. That's what they determined from their knowledge of thermodynamics as applied to light, which was clearly incorrect. And the solution is what we're going to do right now. The solution is, which is the Planck distribution, is that it tails off. We're going to solve for the tail off part. That's what we're doing today. And yeah, anyway, so just that's some historical perspective. I've heard of sometimes people being asked that on prelims. It's kind of expected if you were to get a PhD in physical chemistry, you don't know anything about the Planck distribution or its history, you kind of look like an idiot. So, but now you know it. So that's really all there is. Okay. Now I'm gonna do a derivation twice in two different representations. What I want to do is know the intensity, and again, the intensity of a particular mode, and again, I'll say that's the 600 nanometer mode, and of a particular mode. Notice I'll use some arbitrary designation so that I can then, remember that intensity is proportional to the number of photons, obviously, and of course, the different wavelengths are basically, you can think of these like bins, where the intensity is the number of photons and the bins are the modes, and each has a different wavelength. So anyway, okay, now here's another little bit. StatMech, I've shown you a couple of things about what you can do with Q. I showed how you can get average internal energy by taking the derivative of the natural log. I showed you that if you just take the natural log, you get the Helmholtz energy. There's things you can do with Q to learn what's going on inside of it. Here's another example, and it actually only applies to bosonic particles. Bosonic non-interacting particles, which sounds like, well, that sounds very specific. Yes, but it happens to be light, which is kind of useful, right? So it turns out that the average occupancy of a particular state, given that it's a boson, is the derivative of the natural log with respect to beta. Forget beta. I've seen sometimes people write StatMech and they never, like beta is 1. It just never appears. I don't like that because then your units are screwed up and it's just not really correct. It's just annoying. Anyway, minus the derivative of the natural log of Q with respect to beta times the energy of that particle. Again, the energy of a 600 nanometer photon. The intensity of a 600 nanometer light out of my Blackbody radiator, out of my laser, is the derivative of natural log Q with respect to beta, the energy of a 600 nanometer photon. That's the idea. Okay, and I will need an entire board to do this, so let me move this aside. Exponentials and natural logs, and again, this is why I really like the canonical, because this is not as terrible as you could imagine it could be. Sums out the wazoo, but then sums turns into multiples and yada, yada, yada. Anyway, so let's minus the derivative of beta. What I'm actually doing is proving to you that this statement is correct. And I also am doing this largely just to make sure that your math is okay. It's reasonable to expect you to be able to do this slightly more advanced undergraduate level math. If you are looking at this in cross-eyed, that would be quite bad. So what am I doing? Okay, I've actually gone backward on my derivation. I'm actually using the earlier non-nicer looking form of Q just for the hell of it. Oh, what have I done? I'm missing a natural log. Sorry. I'm trying to stretch and reach up here, and that's kind of stupid. Anyway, I'm trying to make it look nicer. Okay. So again, an infinite number of sums for the infinite number of modes. And these represent number of photons. You can have 0, you can have an infinite number. And what? No, there's the natural. God! Oh, what have I done? I'm so stupid. There's the natural log. I'm an idiot. Sorry. Right, this is Q. Sorry. That's Q. There's the natural log. Okay, sorry about that. Okay, the derivative of the natural log of x is 1 over x. So what I end up with is I can bring down 1 over q. The minus sign can get eaten up. When I take the derivative, I'm going to bring down a minus sign, so that minus sign will wipe out that minus sign. You know, one of the things that always kind of drove me crazy about PChem in general, especially quantum or stat mech, if you lose a minus sign, you're doing it wrong, and that sucks. So anyway, I always try to be careful, because I have to be careful about minus signs and whatnot. Okay, now, the derivative of a function of x, the derivative of the natural log of a function of x is 1 over the function, and then I have to do the derivative of the function, right? So, I'm going to keep the minus sign for now because I haven't done the derivative yet. That will eventually give me a minus sign I can wipe out. And now the natural log is gone because now I'm going to do the derivative of the inside function, and I've written out the derivative on the left. Again, there's an infinite number of sums. Beta n1, f1. Oh, I'm not writing that consistently. I know that's annoying too. Minus beta f1 to n2, and then on and on and on forever in closed parenthesis. Okay, let's see here. Okay, now I can eat up the minus sign. And again, don't forget that there is an infinite number of these summations. Now, it turns out that only one of these guys is acted on by the derivative. If I'm taking the derivative of the term, if I'm interested in the 600 nanometer mode, only one of these guys is for the 600 nanometer mode, and so its n sub j pops out, leaving behind essentially the rest of it. And I'm just going to represent that as the energy of the state. And notice what I've got here. Between this and this, I've got the sum of all possible energies, sum of all possible states, the probability of that state existing, and the occupancy of the jth state, which then, of course, gives me, there we go. So now remember, I told you I was doing something funky here. I told you, where did I do it? I told you this. I just proved it. So that was the idea. Okay, now that I've proven that this is correct, what I'm now going to do is insert this. And then I can actually solve the Planck distribution. So you could, if you, for some reason, just completely believed me that this was correct, or didn't, here we are. Now I can use this because this is like a billion, you know, I could go further with this, but it's a real pain. Now I'm going to insert this guy into here and go forward from there, and then we're going to see that the Planck distribution actually tails off at high energy. So again, what they screwed up back in the day, the Rayleigh-Jeans law, by the way, that's what that was called, applying the equal partition theorem to photons in a box. They just said that if high energy photon can exist, it does exist, and that's ridiculous because you see, remember they said that in their derivation, there's an infinite amount of energy in a blackbody radiator. And we know that you can't just create objects with infinite amounts of energy, and so that's what we're proving. And that's what they got wrong. Let's see, where am I at? Alrighty, so now remember that this is actually going to be the y-axis of the Planck distribution. This is the intensity of light, and hope that I get my natural logs correct. And now we believe that this is the case. Now I've got to take the derivative, and I'm eating the minus sign in a different way. I'm going to have the sum again of all modes, which is unfortunately infinite. Natural log of the partition function. Okay, so the minus sign here was wiped out because I took the natural log. When I took the natural log of this, I brought the 1 minus e to the minus beta energy on top, which also created a minus sign, which annihilated that minus sign. So anyway, So that's the case. You know, if you're doing derivation, if you lost track of a minus sign, you should be worried you're doing it wrong, or you don't understand it. So anyway, just wanted to point that out, that it all makes sense. Okay, now, and then this actually ends up being quite trivial. It turns out that as we think of natural log A plus natural log B plus natural log C plus sum, natural log of A, natural log B, natural log C, they're different because there's different energies. The derivative only operates on the one that has the right energy for the right mode. And so this ends up being, I'll be very formal here. This ends up being, okay, so when you finally, if you're taking the derivative with respect to the zth mode, all the other modes are wiped out, and then you end up taking the derivative of the natural log of the zth guy. Natural log, a derivative of the natural log, you bring down the function. Okay, then you do the derivative of the inside of it, and so that's going to pick up a minus e to the minus beta of j. Then you got to take the derivative. Unfortunately, we have 3 layers. When you're doing a derivative of the natural log, you first bring down, 1 over the function. Then you have to take the derivative of the function. And sometimes there's a derivative inside of that, right? So this is one of those cases. All right, so we have 3 layers, those little Russian dolls that have multiple layers, right? So we have 3 of them in this case. Okay, so this ends up being e to the minus beta over 1 minus e to the minus beta. Okay, you rarely see this put in this form. By the way, this is hugely important. I know it may not feel like it, but this is basically. Well, here, let me show you how I do it. And when I was your age and I saw this stuff for the first time, I got lost, even though it's actually really easy. Where this next thing comes from, you multiply by e to the beta energy on top and bottom. So you multiply by 1, so the top is wiped out. So there you go. Okay, so there you go. There's your boson statistics for population. I think if it's a fermion, I think you end up with a +1, by the way. But we'll do that. That'll be like the last thing we do in here. Okay, and that's actually really it. So what happens is, again, if we look at the intensity of a blackbody radiator, which could be a flash bulb from our camera, which is basically the same thing as the number of photons. And because we tend to plot, I like to think of hot objects producing light, like the sun or my flashlight. Now that would be the visible because I see that. And when we work in the visible, we like to plot things again as wavelength and not energy, which is, again, funky. And so remember that wavelength is actually 1 over energy. And what we get is a rise. This function is a rise. So it says basically when an object is hot and it can produce photons, that's great, but there's a limit. It cannot produce arbitrarily short wavelength, i.e. high energy photons. If it did, the universe would instantly come to an end. So let's be thankful for not all exploding instantly. So now there's a little bit more to the Planck distribution. When we did all this derivation, I never imposed a cavity. Now remember, I told you this already when I had that drawing of the laser cavity. The way I've drawn it is a hot object can produce photons, more and more photons of arbitrarily low energy. That's actually not true if those photons are coming from a cavity like the sun. The sun is so big, a laser is so big, I cannot produce light from the sun if that light has a larger wavelength than the sun itself. That's true. So it turns out that there is a limit to the low energy side. And that's because of a density of states that I have ignored. Eventually, on the low energy, long wavelength, the intensity again comes to an end because I've reached a wavelength longer than the object itself, and the object cannot produce that photon because the photon is too big. So anyway, yeah, so there you go. This is the statistical, it actually really wouldn't be hard to do that. It's just, I don't want to bog you down horribly on some extra stuff, when really the derivation of population for bosons is like horribly more important. And I think we'll have time to maybe see this one more time for electrons and, no, Fermi statistics for electrons and metals, but it's kind of similar. And actually, yeah, I do want to show you one more example of bosons. And this is where it's kind of painful, and I may finish, but I may go kind of fast. A lot of you ended up in solid state groups, so more and more chemists are looking at solid state phenomenon. So some of you are surface chemists, but your surface, underneath your surface is a solid material. My QDs are kind of in between solid and molecular. God knows Cabana is doing all solid state chemistry, solid state physics. So I wanted to show you a little bit of solid state phenomenon here. And for that, I can work here for now. Phonons. Okay, phonons, I'm hoping I don't have to tell you, but I'm going to say it anyway, are of course vibrations of solid materials. And to get you, I tend to forget this myself. Hopefully you've heard the term normal mode before. The vibrational spectrum, now let's go to molecules. When we see the FTIR spectrum of HCl, which hopefully that's something you may have done as an undergrad, or maybe you're a TA in PChem lab, you're going to see it there too, because you're undergrad, you're going to show your undergrads. You know that every resonance is a normal mode. Okay, it's kind of hard to understand that, but in solid state phenomena, it's harder to understand the molecules, except when it comes to phonons. So let me tell you about normal modes as applied to the solid state. It actually makes this jazz easier. Now we all know that we're talking about vibrations, so there's some 0-point energy. Vibrations have 0-point energy. And then you get 1/2, and you get Hooke's law. 1/2 mv squared, essentially, right? So if you're displaced, it's a harmonic oscillator, spring potential. Okay, so I'm going to remind you that the solid, again, let me draw my stupid solid here. Let's think about one atom vibrating, but we're going to have to sum over all atoms. Now, don't write this down right now. I'm going to do something kind of funky here. We have to think about this guy vibrating against all other guys. So let me think about the displacement of one atom from its equilibrium, and I'll represent that as an average. Oh crap, I've run out of, I don't have room, sorry, this board. Anyway, I don't have room to write down what I have to write down. This is kind of long. And don't write this down yet. Okay. Obviously, I have to have a sum for all the atoms in the solid. And we all know that vibration is about displacement. What the hell am I at? Is about displacement from your equilibrium position. So I'm going to represent it that way. Okay. Everything is bouncing against everything else. So I have to have, this is why I told you not to write anything down yet. You had to have room for another sum. Okay, here's the thing I am taking the energy of, but then I have to allow it to bounce against everything else. Okay, and then there is a coupling matrix that tells me, whether it's real or not. So when I'm summing, when the I and J sums are the same thing, that's your normal just 1/2 kx squared potential. And when you're talking about things running to other things, then the I needs to be next to the J. And if when I'm doing the sum, if I have an I that's here and a J that's out here, then this guy needs to give me 0 to say like, no, they're not actually talking to each other, they're too far apart. Okay, so this is kind of like a communication matrix to tell me, actually you're looking at the same molecule, 1/2 kx squared. And that's where most of my energy comes from. But things do bounce against other things, and this tells me whether, oh yeah, you're actually bouncing against your neighbor, that there's an energetic consequence. Then this thing says, no, you're thinking about atoms that are too far apart. They don't really, they're not affecting each other. And what that means is that the coupling matrix is unbelievably complicated, right? There's numbers, I mean, there's a lot of them are 0, but it's rather hideous and unwieldy. Okay, now again, the point of normal modes, if as much as we've shown you spectra and said, oh, every resonance is a normal mode, here's why we do it that way. When you use a normal mode representation, so bad. Okay, if we re-represent the motion of atoms in a certain way, we can turn it into this. We can turn the coupling matrix into something that looks like this, where there's only diagonal elements and everything else is 0. Okay. Every diagonal element is a normal mode. That's what you see in the spectrum. So there's a couple of things about this. This math for normal mode analysis is consistent with the kind of symmetry in mathematics that you observe in quantum mechanics. We're pretty sure that quantum mechanics gives us all the answers we're looking for, so that's like totally awesome. So, and oddly enough, when we re-engineer this matrix using a lot of matrix math, eigenvalue math, sure enough, these are harmonic frequencies that are pretty close to what we observe in molecules and solids. So that's pretty awesome. Another thing is that when I calculate the energy this way, then it ends up being really kind of simple. For any one of these rows, I get the energy of I get a harmonic oscillator energy. So there you go. Yeah. So anyway, that's one of the bigger things I want you to know about normal mode analysis. That's of all the ways to think about normal mode analysis, this one I like representing it this way because I can represent the matrix in a way that's a little bit more just a general expression for energy, which I think kind of makes sense, right? If you're displaced from your equilibrium position and your neighbor is too, well, you might be hitting at each other, there's energy. If I is equal to J, then it's 1/2 kx squared, and I understand that because I've understood springs since I was in middle school. The problem is the matrix, the coupling matrix is like unbelievably complicated. But by rearranging the way that things move, and then finding the matrix that works with that, if you do it the right way, you end up with a diagonal matrix, and that's kind of awesome. The modes would look something like this. Instead of, and so what you change is instead of thinking about any individual atom, and when I drew these little lines, what I was trying to do is to show it like shaking, right? It's vibrating, it's shaking. Instead of that picture, which is kind of intuitive, now that you're in grad school, you hopefully have another set of intuition, which is that maybe each one of these atoms on top is like sliding this way, while the guys beneath it are sliding that way. And of course, that means the next set are sliding this way. So this would be like a mid-range frequency, a mid-range phonon. A high frequency phonon would be where each atom is going the opposite way. That looks like a really high energy, high frequency phonon. So there you go. So when you re-represent the motion in normal modes, your coupling matrix becomes diagonal and your energies become very easy to understand and to work with. So this is what normal mode analysis does for us. You also kind of have to do it this way or it's just not solvable. Nothing is solvable, essentially, like what we're about to do. Okay, so, question.
Why is it an alpha? Why
Now, yeah, so we would have as many modes as we have atoms. So unfortunately for solids, that becomes big, and that'll actually affect the way we solve this, which will be next lecture. So remember, this is like rho I and j, some I, some j, and I'm summing over all the atoms. And a typical object that I would hold in my hand would be about a tenth of mole, so that's 10 to the 23. So I have a 10 to the 23 by 10 to the 23 matrix. So the number of eigenvalues, the number of frequencies is unfortunately unbelievably large. In a molecule, it ends up being 3n times 3n. And so I have 3n modes. And 3 of those modes end up being translations, and 3 of them end up being rotations if it's a nonlinear molecule. The rest is in our vibrations. So, yeah, anyway, when it comes to actually turning this into this, that is unfortunately a fairly complex procedure. It's called the FG matrix approach. F means force constants, which obviously matter. G has to do with the symmetry of the molecule. Highly symmetric molecules have less vibrations than low symmetry molecules. If you have no symmetry to a molecule, you should have exactly 3n minus 6 vibrations. If you have high symmetry, then they can actually coalesce. 2 vibrations may be totally on top of each other, and you don't see them. You see less transitions. Anyway,
I was asking Joseph, alpha, like an alpha, if that is connected to the
yeah. This is one. This is alpha 1. That's alpha 2. Now, and again, you can imagine, just like I have 10 to the 23 by 10 to the 23 matrix. Think about all these atoms and all the ways I could draw these arrows. Yeah, I can draw 10 to the 23 ways. I'm just not, instead of just thinking about one atom moving, when I think of all of them moving, it seems like, oh, well, all of these are moving this way and all of them moving that way. How many ways can we do that? Well, then I start doing this. I can come up with 10 to the 23 different ways for all the atoms to move with respect to each other. That's different than the other 10 to the 23 minus 1 ways, right? So yeah, so an alpha is a mode, and these are just representations of different collective modes that are, the collective motions are phonons. And again, the collective motion is the way that this matrix is being recast into a diagonal form. So instead of being called normal modes, we call them phonons. So, yeah. Well, now let me just tell you where we're going to go with this, because again, this is something I think you would all like to see, and it's kind of important for your just like general education. I'm mostly going to stop there. Let me just tell you what we're going to do next time, because it's going to be a while before we meet again. And I also want to do some solid state phenomenon, because I think about half of you are in solid state groups or kind of associated with solid state types of things. What we're trying to do is calculate the heat capacity. All right, so what I'm going to do is I'm going to calculate Q, given that energy equation, which I'll use the correct language and call that a Hamiltonian. What I'm going to do is calculate the canonical partition function. Now from this, I'm going to do some tricks like calculate the average internal energy. And then what I can do is I can take that average internal energy and take the derivative with respect to temperature to get the heat capacity at constant volume. Now the reason that this is important is that Einstein did this and made an assumption. Einstein said that in a solid, now you got to, all right, so Einstein was wrong, by the way. As it applies to chemistry, a lot of what Einstein said, actually almost everything Einstein said was wrong. All of his theories do not apply to chemical phenomena. They apply to galaxies and spaceships going the speed of light, which he was kind of obsessed with. All right, what he got wrong about solid state phenomenon was that he thought that atoms vibrated in the solid state. Everything vibrated with one frequency, and that is not correct. There are low frequency modes and high frequency modes, which I just drew. What I just drew there, did I delete it? Yeah, I just deleted it. What I just drew there, Einstein did not know that. And because of that, when he solves the canonical partition function with one frequency, he gets a heat capacity versus temperature that was almost perfect. Almost perfect. And here's the data. Here's the data. And, they get this result, and they're like, nailed it! Did he? Did he nail it? No. It wasn't exactly perfect. He didn't get it right. He's so close. At first, everyone's like, yeah, this is great. And people kept looking at this. They're like, no, it's not exactly right. Heat capacity of solids at low temperatures scales as T to the 3. That's like the Dulong-Pettit law, something like that. Einstein had temperature scaling as exponentially, something like that. I'm maybe getting it slightly wrong. We're actually going to prove this. He got it, it's just not quite right, and so the data don't quite fit. The solution, which was come up by Debye said that there's a range of frequencies. Low frequencies being when all the atoms are like doing this, and higher frequencies where every atom is moving in a different direction. And when you consider a range of frequencies and a high frequency cutoff, his was perfect. And what's important about that, by the way, it introduces the concept of density of states. And density of states is unbelievably important. I never read anything where I don't see the word density of states. So I want to cover that just so that you kind of see density of states and the things we do with it. The negative, though, is that density of states is like the word adiabatic. It has like 6 alternate definitions, and none of them are actually consistent, or they're very loosely consistent. So while I'm going to show you how to solve the heat capacity of a solid using the density of states, which is correct, understand that when you see density of states applied to other systems, that they have nothing to do with each other, except the words. So anyway, so I went over. So I'm kind of, again, I'm just trying to immerse you in this stuff, try to get you to think correctly about chemical phenomenon. I don't really care if you get out of here and don't remember this, but it's just how to think about states, how many states you have, how we represent our spectra, what that really means. That's kind of more the point. So, and I'll let you know about my cue. Alrighty, anyway, so out, get out. I have a party.